so that a lè tètè ṣiṣẹ́ lórí ẹ̀ pé kó fi gbogbo àwọn time tó pọ̀ láti yanjú. So correctly, nǹkan tí mo ní is just the algorithm. So I don't know if you have done anything towards the analysis or and of course group wo leléyìí náà.
Group 1. Group àwọn Dr. Lugaf.
Okay. So ẹ̀yin méjì lè wà ńbẹ̀ láti ní group yẹn wà.
What of it?
Okay. So the other group yẹn ni group àwọn Dr. Ogunṣọlá, Dr. Alepo àti Dr. Lọ́nàrí.
Yes, sir.
Correct
Yes.
one. Okay. So
So,
gbọ́dọ̀ náà bá tẹ̀lé dé. Àbẹ̀rẹ̀ sí bẹ̀rẹ̀ rárá.
At the proof of boundedness by
Ẹ jẹ́ ká restructure títí. So let's see how we went about it. Ọjọ́ how correct this is.
okay, sir. Can we start from the algorithm or from the lemma?
No, the algorithm lesson.
All right.
So I just pé ní ìsìn we're using today for this group. So tó bá di next week we're expecting the same thing látọ̀dọ̀ yín náà.
okay, sir.
Okay.
Now, so this is the algorithm. So can you take us through the algorithm? Let's see what's out there. What is the algorithm about, and what are you trying to achieve?
This algorithm is about motor inclusion problem. This algorithm is about it's a natural algorithm. Or let's just say two natural algorithm. Yeah. With motor inclusion problem and yeah, and also we have forward backward method and semi group mapping.
Forward, backward, forward. Forward, backward is in 3.3. 3.4 is a combination of forward, backward, forward, which is also called SING extravariant method.
Yes, sir.
So the SING extravariant method is called the forward, backward, forward. But
Okay.
ZN 3.3, that's what is called forward, backward.
Yes, sir. So this forward backward, which is called motor inclusion problem, and
which is for solving, it's not called.
for
It's for
solving motor inclusion problem. And here we have SING.
Hello, sir. Can you hear me, sir?
Yeah.
Hello, sir. Can you hear me?
Yes, sir.
Yes.
Can we be asking question while the presenter is presenting? Because I have
yes,
spotted
you can ask questions so that we can learn. Yeah.
I've spotted
Okay.
that 3.3 is wrong. ZN. There is no forward there. There is only backward. Check. ZN is wrong there. It's supposed to be I plus RA inverse into I minus RB.
That's true. Should be I plus RA inverse, then I minus RB WM. Yes, that's correct.
That is wrong. That is my observation for now.
Yeah, that's a very good observation.
Thank you, sir.
So apart from that, I think and also the phi and there was a phi in 3.2 has no place in the algorithm as of now. So for the inertial extrapolators, I think what we can find there is theta n and alpha n, not theta n and phi n. So for 3.3, there were theta n and alpha
Standard.
n. Y 3.1 and
Maybe alpha
3.2 as theta n and phi n.
That's
So-
another error.
Yeah.
Well, this should be supposed to be fine.
These things at this stage, the
What's-
essence of day 3 on this work is to be able to see out all these little stuffs. So when you work on them together, whatever is missed by A should not be missed by B. So, and that's the essence of the collaboration. It's all about one person doing this thing. So, Tabaye pé gbogbo wa fẹ́ mọ̀ and we want to go at the same pace, we should be doing these things together. And even if your Zoom is not going to grant you more than 40 minutes, it's a whole lot of time to have a discussion on this thing. So, apart from having this general discussion group, I suggested the other time that whatever group that Bani, let's try to maintain a close knit, have a time that will be having a discussion, whether it's in the morning or whatever time. It's just a dedication of a few period. Cannot really do it. Okay, now if I see something, I'm able to do this. Even if I'm going to call someone to it, I've done a major chunk of the work, then I just call in someone to help me check. And that will be my collaborator. But for now, we're working hand in hand. That's in the job way. We're able to, at least to some extent, Ali Daduro. So that's that. While I said you should take us through the algorithm, it's for those purposes that we are saying. If you go back to the initial step, it says given phi 0, 1, mu greater than 0, theta greater than 0, phi greater than 0. So when we try to see if those things are part of the algorithm, and of course there's none. Like we can only find theta, we can't find mu. Also as well, I think we can find phi as well. So the initial points that you have chosen in H are also not correct. You have x minus 1, x naught, and you went straight to x2. I think it was supposed to be x minus 1, x naught, and x1.
X1, yeah.
And that would be that our n is starting from 1. So that would mean that our n is starting from 1. So those things are very, very important and very key. I mentioned it shows that you understand exactly what you're putting out there. Okay, so for now, those are the things that I have seen. Okay, and as well again, lambda n. What is the essence of the lambda n there? Lambda n, if lambda n is a coefficient is part of 3.4, then it means that the controlling parameter, the controlling sequence or whatever for A and B in 3.3 also has to be lambda n. So this is another error. Lambda n also has to be a part of the forward backward. If lambda n is part of the senc, then lambda n has to be, that should be the control parameter for both operators A and B. Is Dr. Ogunsola with me?
Yes, I am.
Is what I said, did you find that correct or what?
Yes. I did.
So that's another error. So lambda n, that Zn has to be I plus lambda n A inverse into I minus lambda n B. So that should be, because if the coefficient of the coefficients or the parameter is lambda n in 3.4, or we say the parameter in 3.4 should be R as well. So it has to be uniform. The same thing what you're saying in 3.3, unless you're doing something different. Or maybe R and lambda n have a relation. So could be something different. You might be doing something that makes sense only if you work with it and there's no issue working with those things. So table shade something new. So currently, because I use money pay the parameter that is controlling A and B in 3.3, therefore Zn has to be the same parameter in 3.4 for Yn. So for me, That's an error. And the update that you described in 3.5, I suppose the update is also supposed to be lambda n, not
Lambda,
mu n.
yeah.
So how you proceeded now to obtain the bandedness, even when the algorithm is not correct, remains to me a mystery. I don't know if it is to the other people. And as well, 3.1 and 3.2, I don't think they're going to be like that, because 3.1 now, theta n seems to be the momentum for xn and xn minus 1, and alpha n is momentum for xn minus 1 and xn minus 2. But if you look at the online rule in X, remove the distance, remove the color so that we can see it properly. For 3.2, remove remove the color in 3.2. So the online rule in 3.2, which we have said is wrong, is supposed to be alpha n, not phi n. That's not the only thing. The definition there has xn and xn minus 1. Meanwhile, phi n is a momentum for xn minus 1 and xn minus 2. Who else is saying that? Or who else agrees with me on that?
Yes, I do.
Please come again.
Yeah, if you look at step 2, 3.3 there, the first line, that is Wn, which is xn plus theta n into xn minus 1 plus alpha n, xn minus 1, xn minus 2. So we have, for those extrapolators, theta n and alpha n, we have that theta n is momentum for xn and xn minus 1, and alpha n is momentum for xn minus 1, xn minus 2. So if you now go to the online rule, for theta n, whose momentum is xn minus 1, you are going to see that the minimum is taken over theta and epsilon n over norm of xn minus 1, which is according to what theta n is controlling in 3.3. But if you go to 3.2, we have already said 3.2 currently is correct. It's wrong the way it is. It's supposed to be alpha n. And secondly is that the maximum should be taken over minus alpha if it's alpha, then and minus epsilon n all over the norm of xn minus 1 and xn minus 2, not xn and xn minus 1. Did you get that?
Yes.
Yes, sir.
The explanation is there.
Okay. So that's another error that has to be corrected for the group. So at first, it means that the algorithm is wrong, but let's see what you're able to achieve in terms of the proof of the bandedness. Let's see how you moved. So then we see if you need to add anything again. So currently I'm going to stop. Allow the other members of the meeting now to check line by line to if there's any error that they have made. So
Hello,
the
sir.
presenter can take us through.
Hello, sir.
Yes, sir.
In that lemma 3.3, the first statement there. So will it allow us to continue when the Zn is wrong? Because Zn is still 1 minus Ra.
Yeah, let's assume that they already know the correct thing now. Let's just work with yeah. Yeah, there's an algorithm like that actually, but it's not forward backward. So this is not this is just forward. I don't know even how to describe it, because it has minus. The forward there is as a result of the inverse minus 1 there. So now that you're having I minus RA, so probably you call that a modified forward backward. So but what we intended is a forward backward and then forward backward forward. So that is forward backward coupled with a Senk algorithm. And the essence of using a Senk is such that the other method, the operator in the backward evaluation is monotone, not strongly monotone or strongly inverse monotone. So the essence of having the Senk step is such that we can have, just like we used to say for variation equality, that the gradient method can only work for strongly monotone operators. If you want to have a monotone operator that is not strongly or strongly inverse strongly, then we have to use the gradient method. So go ahead.
Yeah, from this lemma, we assume that the condition of the assumption. So we have not read out the assumption 3.1. So let Wn and set n be a sequence generated by the algorithm 3.2. If there exists a subsequence, this Wnk of Wn that converges weakly to some point, S bar belongs to H, which is a bar space, and limit of Wnk minus Znk equals to 0. Then we have S bar of Vi of H comma B, which is the solution set. That is, S bar is a solution of the variational inequality problem defined by the operator B. So by proving this now, from the step 2 of algorithm 3.2.
Only decided to take a pause. I believe there is a mistake there, and no one is pointing it out. Does anyone
Yes.
know what the mistake is?
There's a mistake. There's a mistake there.
Okay.
The mistake I can spot now is the use of algorithm 3.2. Is it labeled algorithm 3.2 or algorithm 3.1 in the lemma? Is our algorithm called 3.2 or 3.1? Maybe the presenter should educate us. You're right. The first one okay, use 3.2. Okay, all right. So you can continue. Because I thought you used 3.1.
No, sir, 3.2.
That's not the error that I'm seeing here. I don't know. Okay, check again. Check the hypothesis of the lemma itself. So there's an error in the hypothesis.
Yes. Another error I suspect is that assume that the condition in assumption 3.1 holds. He has not given us the condition.
Yeah, he mentioned that they have not written the condition. They mentioned that. That's still not the error. Is Dr. Aluko there saying it?
I'm not spotting it.
Okay, let me point you to where the error is.
Go ahead, sir. I don't see any error for now.
Okay. Then X bar is in Vi H comma B, which is a solution set. However, solution to what? Check the statement that followed that. That is,
S bar is a solution to the variational equality problem defined by operator B.
however, the problem is not variational equality,
Inclusion.
but variational equality problem.
Variational inclusion problem.
Inclusion. Oh, yes, that is true. That is true.
Forward, backward is not used to solve a variational inequality problem, but variational inclusion.
Yes, sir.
What we use to solve variational inequality is projection gradient or projected gradient. I hope that is clear. These things, yes, we mentioned them from the beginning of the class. If you see something like this that has PC, then we know that they are about to solve what?
Variational inequality.
Variational inequality, even though we have not mentioned anything like that in this class, and probably maybe majority of you have not seen it. We can use something PC as well to solve equilibrium problem. We can use something that has PC also to solve equilibrium problem. So in that case, we'll be taking the derivative, the second partial derivative of the bifunction. So maybe one of these days we're going to work on it, and then not as a group, maybe the individual classes I do have as well with some of us that are here. So I'll just give you an algorithm that has to do with that and give you some papers to check. So we use something that has PC to solve not variational equality, but for what? But for equilibrium problem. Yes. So, but anytime you see forward, backward,
or anytime you see PC, your very first point of thought is that this should be what? Variational inequality. Exactly. And anytime you see forward, backward, like we have it in Zn 3.3 there, the very first thought should be variational inclusion. Of course, it has not been used to solve any other thing. To budget, solve minimization problem. For instance, MMRE partial derivative there. So instead of that B, it's going to be a partial derivative. So those things, go back on those videos, the previous ones that we have done. Here quickly, algorithm. Very first thing, algorithm without even putting any pen to paper. So those things, even to algorithm, for instance, to equilibrium problem. If the algorithm is to be used to solve a monotone equilibrium problem, if the algorithm is to be used to solve a pseudo-monotone equilibrium problem, you are going to know. Báwo la lè ṣe máa mọ ìyàtọ̀ ní méjèèjì? Títí kí lórúkọ ẹ̀? Ẹ jẹ́ kí n sọ títí pseudo-monotone equilibrium problem. Ní tẹ́ máa fi tètè mọ́ ẹ máa rí proximal operator ń bẹ̀. Argmin, tẹ́ bá ti rí argmin, tó dẹ̀ jẹ́ wípé equilibrium problem ni, ẹ ti mọ̀ pé that equilibrium problem is going to be pseudo-monotone. So let us stop there so that we can continue. So the error now is variational inequality. But meanwhile, the algorithm is for variational inclusion problem.
Thank you, sir.
Okay, thank you.
So, by proving this now, we are sorry for I think this typographical error.
Sorry to interject again. I think I want to agree with Dr. Gunshola that since Zn is incorrect, every other thing that follows most likely is going to be incorrect, because that's exactly what I'm saying now. Using the resolvent identity for monotone operators, it follows that that thing is supposed to be I don't think it is correct the way it is. So we're not going to obtain that second step from the definition of Zn. I don't think it's going to be like that.
Supposed to be I minus RA Zn.
It's contained in, it's supposed to be I plus RBN. I minus RBN is contained in Zn plus RAZN. Zn plus RAZN. I think it's correct the way it is. Correct, but the only thing is just that the plus in the I minus RA, we keep plus one, man. Because if you look at that, A there is a set valued function. A is a set valued function. So tabagbe I minus RA to inverse and let's see left side. So we're going to have I minus RA of Zn. Correct. So, but which means I minus RB of the UN would be an element in Zn into I plus RA. So now Zn, let's see other side. So we're going to have I minus RB of the UN minus Zn contained in R of AZN.
Yeah. So from this,
the proof is very, very wrong. There's no going forward. There's no going forward in this sense. The proof is wrong. Also, since B is assumed to be Lipschitz continuous and pseudo-monotone, in the first place, Cousin got German pseudo-monotone for the operator B. So you're looking at an operator that is monotone and Lipschitz continuous. So that's one. Then under the assumption that you can't, I don't know how you obtained that 0 is in zero is in AX of BX from an argument to an argument. So like
No, there's no way. I don't know how you have achieved this. This is not the proof. This is not the proof to show that uh, 0 is the inclusion point of that sum of operators. That's not the proof. I guess we had a paper on this. And the paper kan lórí nǹkan ìtẹ́lẹ̀ àbí?
No, sir.
Mo send paper ta rí nígbà yẹn, was it? Ó rẹ̀ pé paper yẹn was about racial equality and fixed point of an non-expansive semigroup. Is that?
Yes, sir.
Okay. So, but there have been several papers that will share on variational inclusion problem. So how they obtain the solution set, the proof to the solution set, you should get it there. So this is wrong. You are wrong entirely. There's no way you can achieve this here. Láti show pé kíní is a 0. Ó máa involve further calculations tó máa involve norms and inner products. So there's nothing like that here currently as it is. So eléyìí ò lè jẹ́ solution. So lemma 3.3 in its entirety is wrong. And the proof as well is not correct. So please go over that proof again. Let's see if you have other proofs. Ẹ lọ wá mọ́ ṣe proof yẹn.
Okay, sir.
Again, lemma 3.4, I don't know if it's necessary. I don't think lemma 3.4 is necessary. There has been a lot of proof from lemma 3.3, lemma 3.4 rather. Àwọn paper tẹ̀lé cite wà fún. I don't know if I'm correct. I think you should be able to cite some papers for lemma 3.4.
Okay, sir.
Ẹ̀yin mẹ́ta lẹ tún wà ní group nísìnyí, ṣé ẹ̀yin mẹ́tẹ̀ẹ̀ta lẹ agree pẹ̀lú mi? Dr. Gafar, ẹ káàbọ̀. I guess his network is not fine. Ṣé Dr. Ogunṣọlá agree pẹ̀lú mi?
Yes, you are right, sir. You are
Okay.
right.
So let's move to another lemma. And even at that, look at Keto loans and around that thing. We might find as mistake now. Look at that thing. It's at some point, tau is subsequent with n. Maybe what you saying. I think tau k no again. So those are the things that you have to make sure that you take out. And when you're correct, if you look at also since tau n is greater or equal to 0, it follows that lambda n is a non-decreasing sequence and lambda n is less or equal to lambda naught plus. Okay, I've seen the essence of the key. So I think that makes sense. But, okay, yeah. But I don't know if it's supposed to be k from k to n minus 1, but wherever it is. No, I don't think that is correct. I don't know if it is correct. I don't know if it is correct. Well, let's proceed. I'll check. But just like I said, I think all I could prove it to one because no, I don't see the reason to prove it again. Let's move to maybe lemma 3.5 for there's another one. Okay, now let's see this one.
From lemma 3.5, let Fn be a sequence generated by the algorithm 3.2, and we have S star which belong to omega, and omega is generated as the solution set of our algorithm. So then, for all n is greater than or equals to n naught, so we have this. So since our yn is our Seng algorithm, so we have yn minus S star square. So will be less than or equals to this. after open the square norm. And then we have our lambda to be in 0 and 2. So by proving this now, so we have our yn to be this. So then we have our x to be this, and our since s is in what? It's in this, so our s is also in the omega. Our y star.
No, it's that way. It's the other way. It's the other way. It's the other way. X star in omega will imply that X star is in that, because I don't know if you have defined omega as the intersection. Omega should be a common solution to the variation inclusion problem and the fixed point problem. So if X star is now in that solution set, there is it's clear that X star will be a solution to the variation inclusion problem. This is set theory. So if omega is the intersection of the two problems, the solution to the two problems, so a solution, an element that belongs to the intersection of both, will be an element in both sets. So if X star is an intersection of the solution to the variation equality problem and fixed point problem, so clearly X star will be a solution will be a solution to the variation equation problem. So implication X star is in omega implies, so it's not since again. Dr. Gushola, are you with me?
Yes, sir. Yes, sir. Yes.
Dr. Aluko, so correct?
Yes, so correct.
Point.
Okay.
Point.
Okay, thank you, sir. So then we have so we have this. We have inner product of b of x star, comma yn minus s star is greater than or equal to 0. So using the pseudomotonicity of b.
We're stopping now. At a stop by. The error is just one too many. So we're going to stop here. Shemo.
Okay.
Because the operator is not pseudomonotone. Again, the operator is what? Monotone and loop is continuous. So we're not going to have this. And yet again, even at that, cartoon learn again. But even if the operator B is pseudomonotone, it's rather supposed to be B of yn, comma, yn minus x star, not B of zn. Where's zn coming from? Not at all. So please go over again, correct your algorithm, and do the right thing.
All right.
So this is where we're going to stop for today. So I don't know if I've been ruthless or I was very nice. So the second group, you're saying how it is. So please take your time to do what is correct, please.
Okay, Oda. Thank you.
Thank you, sir.
So they should go and correct then the following week to because you're not present next week. Should it be? No.
All right.
So, but before we go, kí ni ti tọ̀dọ̀ yín wà about? What are variation equality tọ̀dọ̀ yín?
No, variation inclusion using
contraction method.
Contraction method, thank you.
Projection contraction, yes, that's true. That's true. Yes, that's true. Yeah. So we'll be expecting your presentation next week.
All right, sir.
Kan sọ̀rọ̀, mi ò sọ̀rọ̀ níbi kí lórúkọ ẹni níbi conclusion lemma 3.5. Even this conclusion is wrong. Irú conclusion tó ní ìsìn should be a conclusion for people that are working with projection contraction. Lè rí irú conclusion yìí nínú ẹni tó bá ń lo SENG. This conclusion is not for SENG. I don't think this will be a conclusion for SENG. I don't know. Ẹni tó bá ń ṣe projection contraction method ló lè ní irú conclusion tó ní nínú lemma 3.5 yìí. So this is a conclusion from that.
Ẹ bá wo 3.6 kẹ́ tó lọ sá.
Listen, kò sí nǹkan tó simple to 3.6. Ilé ń ṣe kò sí nǹkan tó máa simple to ilé. This one is cheap. Ilé ìtura pé máa live directly from the paper.
Doctor. I go wait. I respect you, sir.
Ẹ jẹ́ ká parí bí báyìí ni.
Lemma 3.6 yẹn direct lift ni. Èmi náà ti rí
Ẹ̀yin
ìwé.
ò ìyẹn ò lè kò yìí kò
Mi ò
sẹ́ṣù
lè
kò
fún anybody
sẹ́ṣù
problem, kò lè fún problem, kò lè bá náà problem. A kàn máa
but
gbà ẹ́ kọ́ ni.
even wọn ẹ wá wo àwọn gangan náà ṣe nǹkan ṣe mistake ń bẹ again gbé
This
padà
3.6 again.
yes 3.6
Mistake wo sir?
ó yà sùn sísàlẹ̀ wà rí sàn.
Àbí dókítà wà lọ́dọ̀ ìyàwó wọn gbà tí wọ́n ṣe ni.
òun lélẹ́yìí òun rè we now consider that WN is an initial combination look at that WN again níbi àwọn extrapolators yẹn again wọ́n tún wrong theta n and phi n kò síbi
Báyìí ni kó síbẹ̀.
alpha n dẹ̀nà mú wá láti bẹ̀rẹ̀.
Okay.
mo sọ fún
Yeah.
Dókítà ẹ̀ mọ̀ wé jíwò rárá.
I think the advice given by Dr. Yewole should be taken to. Before presentation, the group has to meet. Bóyá ó dà pé Mr. Kajola nìkan ló ṣe eléyìí ló fà. Táwọn gbogbo bá meet wá ti point out one or two things.
Dr. Lugavo lásìkò.
Mr. Kajola ò mọ̀ wé jíwò rárá.
Lugavo lásìkò.
Jíwèé wò rí rárá.
Hello, sir. Àwọn àṣẹ àtúnṣe síta, thank you, sir.
All right, sir. Kẹ́ lọ́jọ́ rere o.
Yeah, ẹ ṣé o, after a very long time. Okay.